giving. So yeah, my name is Bas Steunebrink, pronounced the Dutch way. I'm co-founder of the AI startup Nascence, where I'm director of AGI. And this presentation will be about AGI from a real-world perspective, namely from the perspective of its industrial applications and what it means for AGI in terms of requirements, architecture, and deployment. So let me start by giving a very short background and context for what I'm talking about. Although this is, of course, not a sales pitch, it's only fair to acknowledge upfront that our work on AGI is driven by commercial interests, but that, in my opinion, is exactly how it should be, because we must try in the real world what works and what doesn't, and let those lessons feed back into our research. And we believe that the vision of AGI cannot be fulfilled in vacuo, nor from simulated games, but requires this feedback from real-world industrial projects. So yeah, our main business activities so far in the space of monitoring for anomalies and defects, predictive maintenance, digital twins, and industrial process control. And here we bring our expertise in deep learning, reinforcement learning, and evolutionary algorithms to automate and optimize industrial processes that are too difficult for human engineers to improve any further. The grand vision, however, remains general AI, exactly because increased generality will decrease the cost of deploying and maintaining our automation solutions. So we want to become continually faster and cheaper at tackling new and sustaining existing automation challenges. AGI, as the name implies, is the endeavor to replicate human-like general intelligence in machine. But why do we want such AGI actually? Surely we are not chasing the Hollywood fantasy of cute androids that just want to be loved as humans. No, we are targeting real-world intelligent systems that add value in industry, exactly because there are so many tasks that human workers cannot or should not have to perform. And so here we list the properties that are relevant to the specifics of AGI in the industrial domain. First, robustness to change, to drastically reduce reconfiguration downtime whenever the plant or operational conditions or requirements change. Second, data efficiency, to acquire relevant data autonomously, bottom-up and in real time, and bypass lengthy data collection processes and other impediments to speed, and reduce reduce to zero the dependence on big data. Third, rapid innovation to adopt principled short innovation cycles. AGI can guide the proof of concepts, POCs, and then transfer them immediately to production. Fourth, the safety aspect, we ensure that AGI complies proactively with verification and validation procedures and is certifiable at any stage of its life cycle. Fifth, the open systems of systems. We reduce the operational silos. The AGI integrates with other systems, leverages human domain expertise, and opens its own expertise. And finally, the capitalization. The AGI creates actionable knowledge. This is a key asset that is continually updated, expanded, and shared with other systems, with other engineering processes, and with stakeholders. So let us get a bit more concrete. Nascence has developed an AGI technology called Adaptive Rational Core, abbreviated ARC here on the slide. This is a general control system, and this is a depiction of how this AGI operates in an industrial setting from the perspective of the AGI itself. So we'll treat the owner perspective later. First, we note that the AGI consists of two components here in orange: a fixed controller, which is interacting with the plant as well as its owner, and an adaptable model of the plant, which contains all the knowledge of the AGI. So I keep talking here from the perspective, from the industrial perspective. So I say plant model, but you can read world model here as well. It is the controller that interacts with the plant in the standard way using sensors and effectors. But the AGI also interacts with its owner, who can change the mission of the AGI at any time by specifying new goal states and new constraints or forbidden states. Conversely, the AGI constantly reports to its owner what it is planning to do and how confident or confused it is. These two components of the AGI, the controller and the model, they interact in three ways. And these are the three parallel main activities of the AGI, namely planning, predicting, and learning. First, the goals specified by the owner are propagated backward through the planned model in a process called abduction in order to come up with plans to execute in the plant at the right time. Second, the sensory inputs and inferences are propagated forward through the planned model in a process called deduction, generating further predictions about the plant, which of course have to be checked for conflicts against the AGI's plans. Third, any failed predictions or other surprising events signal that the model is not complete or accurate and thus needs to be adapted, which is called learning, of course. And it's these three activities together that can be summarized as one overall activity, namely that the main business of an AGI is to perform work on command, which is the dynamic coupling of the ever-improving knowledge with the ever-changing missions imposed by the owner at any time. So this is the central takeaway message actually of what is real-world AGI. If nothing else, please remember that real-world AGI is a system capable of performing work on command. Right, yeah. Sorry, it wouldn't progress. So now you may wonder what kind of magic is going on inside the planned model or world model. So let's connect it to reality a bit. We see the world as a nested graph of causes and effects at a high level. For example, we see goods moving from plants to relays to hubs across pipelines, tracks, etc., etc. And also within a plant, stuff is moving across the shop floor, partial products are moving between stations. And so if we look closely at each node and each edge of a graph like this, we see that what happens there is influenced or even disrupted by myriad actors and events, which are deeper down, affected themselves by deeper causes, such as the behavior of markets and weather. Now, any human or machine that understands how and why things move and how and why things are disrupted will need to learn continually to deepen its knowledge of these causes and effects. And so this is then the first flavor of what AGI technology offers in the real world is continual monitoring with deepening understanding. So let me give three concrete examples of how this is valuable. Obviously, first, to monitor disruptions with lead time. So if disruptions can be predicted beforehand, alerts need to be raised and contingency measures need to be planned and they need to be shown to the operators. On the other hand, sudden disruptions may happen at any time. Of course, a system needs to recognize those and alert and also plan immediately mitigation measures. And third, what if scenarios can be considered. So the owner of the AGI, the owner of the plant, can propose counterfactual tasks or modifications to the graph that we saw before, which is basically introducing disruptions and ask the system how to respond. The system responds then with predictions and plans on how to deal with that hypothetical situation. And so from the owner's perspective, he doesn't need to get like a full-fledged AGI into his plant, into his factory all at once. That would be kind of scary, but instead the value can be delivered in a collaborative manner progressively as follows. So first, there can be a modeling phase where the AGI produces, observes the operational data and produces auditable and shareable models. And this is immediately valuable to the owner because it generates reusable and shareable insights into his own business processes. So sometimes this is also called digital twinning. Second phase will be once these models have been verified to be of any accuracy, the system can be connected to the actuators, but not really. So make the system think it's connected to actuators, but it's not really, and then interpret the output of the system as recommendations of corrective actions. These are shown to human operators who can then verify them at their leisure. And this way, trust can be built in the AGI's proficiency. And a conclusion of that would constitute a proof of concept. Once this has been verified and validated, the technologically speaking, a trivial step, but from a mindset perspective, could be a big step, is to then actually put the control system in control, so let the actions of the system actually go to the plant, to the machines. And AGI is now connected, taking the actions, and the value here is, of course, the cost savings on operations. But since we have a general intelligence with knowledge that can be capitalized upon, we can go further and we can specify, for example, additional targets, additional quantitative targets, and the machine can optimize its actions, come up with better plans, and thereby save costs on resources. And this goes further and further into the future without any disruptions. You now have a machine that can adapt also to new requirements and constraints, and integrate itself into the larger system of systems in the plant. And this way you obtain operational agility with minimal disruption. And then, of course, a new cycle can start as well with increased scope and increased breadth of missions. So this brings us to the real world value, the value of AGI in real world industrial settings, as opposed to its supposed value in Hollywood fantasies. And this is really the value proposition for AGI is really to own an autonomously adaptive system capable of performing work on command. And we're very serious about all these terms here used in this value proposition. The plant owner can really own the know-how, how to specify goals and constraints and targets at any time to the system, and the system will immediately couple that with its latest knowledge to come up with new plans to control his plant. And the knowledge of the system is always white box and verifiable, so it can audit also its reasoning. The system remains continuously adaptive. I'll show how that technically works in a minute. The system learns on the job and will not suffer from retrain, freeze, deploy cycles that are inherent in typical machine learning techniques of today. And really here, again, I keep emphasizing the work on command is that the system really predicts, simulates, recommends, plans, and acts as you want, coupling its latest world model to its latest goals at any time. Yeah, maybe I will skip a few of the, looking at the time, a few of the use cases in industry. Let me go a bit more into the, because this is an academic conference, go a bit more into the technical details of how this works, the adaptive rational core. So, I'll explain ARC from 3 perspectives, which I believe is warranted because the technology is quite different from current mainstream AI approaches, including machine learning. So the perspective on structure explains how plant models are learned in a dynamic and modular way. The perspective on process explains its continual learning, how its continual learning capability works. And the perspective on theory explains how the technology is founded in principles and insights from the field of categorical cybernetics. So from the structural perspective, a model in ARC is populated with rules, potentially massive amounts of them, which are exploited at any time by the controller to predict and to plan. One rule has several inputs and an output, depicted here as dots. Rules also contain a transfer function to transform inputs to output and timing information about inputs and outputs. And one rule basically says that when my inputs occur within their respective time windows, then my output will occur within this and this time interval. So the rules actually, they embody contracts, meaning they constitute formal guarantees on the coupling of domains and codomains. And this will come in very handy in the theory perspective later. Rules are symbolic numeric hybrids based on linear arithmetic, but the details are out of scope here. But at the end of the presentation, I'll show you where to find the details if you're interested. But it's important to note here that rules are non-axiomatic, meaning that truth is a matter of degree, sanctioned by ongoing experience, and always subject to change due to unfolding circumstances. So rules, these rules, they are added and deleted and vindicated and falsified by experience. There's no need for an a priori fixed model architecture. Prior knowledge can be imparted to speed up or focus learning, to impose constraints or optimization targets, to integrate domain expertise, and to interface with external subsystems. The dynamic modularity of rules means that models 1 and 2 here capture two different perspectives on the same plant, yet reuse common parts as shown in orange. Once the orange rules are learned as part of model 1, they do not have to be relearned, but can be transferred to populate model 2. And this is possible because rules capture world knowledge in a completely task agnostic way. Now the process perspective on ARC, the lightning strike event that causes a new rule to be created, as depicted here, is the surprising success of a goal or the failure of a prediction. It is such events that signal that the model is inaccurate or incomplete, and therefore a new explanation of the surprising event is created. This explanation is created by taking salient events from the input stream as the left-hand side of a new rule and the event to be explained as its right-hand side. This rule creation process is erring on the side of inclusion. Some inputs may turn out to be irrelevant, as experience shows that their occurrence or non-occurrence does not help in predicting the output. Over time, rules consolidate to form the explanations of the true causes of events. This continual learning process means that ARC does not require troves of data upfront, and the rules are fine-grained and modular, facilitating focus training, reuse, and robustness to changing environments. How are these rules then exploited for control, for doing the work on command? Then we switch here to the theory perspective on ARC. Fundamentally, control is achieved through the synthesis of two important fields, namely control theory and category theory. From control theory, we know that actions can be computed by combining a forward model and an inverse model. The forward model in blue takes a sensory readout S and computes a prediction P, and the inverse model, shown in orange, takes a prediction P and a set point G and computes an action A. Thanks to insights from category theory and leveraging a class of components called optics, we fuse the forward and inverse models into what is called a lens, which is a compositional object that supports both deduction and abduction using the same signature as the forward and inverse models together. And so we just need one rule R here in white in the shape of a lens to implement both deductive and abductive capabilities. Implemented as lenses, these rules are compositional and can thus be chained while preserving the provable properties of the system as a whole. And so, leveraging the theory of categorical cybernetics, ARC implements the capability to perform work on command by dynamically coupling the ever-changing knowledge and the ever-changing missions in an open-ended control loop. ARC is safe in both the obedient and the prudent sense, namely, it will do what you told it to do and it will not do what you told it not to do. The corresponding contracts can be verified and are preserved during operation and further learning, thanks to the compositional properties inherited from categorical cybernetics. On top of this, and we did not go into this, ARC evaluates its own proficiency by identifying control loops, computing their reliability as well as their coverage. And with coverage, I mean the volume of the state space where the control loops are effective. These results are continuously and proactively reported to the owner, who can thereby understand how the adaptive rational core understands its environment and what can be done with it. And so where does this endeavor lead in the future? Here we're moving into the territory of what's called Industry 5.0, that of autonomous factories, where low latency is of greater importance than high throughput, where the reconfiguration downtime is minimized, allowing mass customization. And this is not a concept that we dreamed up ourselves. In fact, major players such as General Electric and Siemens have declared the importance and value of this future. For example, General Electric writes, the goal is to have a system of systems that configures itself to any need and improves itself over time. And Siemens, for example, writes, we're on the way to automating the automation. AI-enabled systems are aware of their environment. They're capable of finding solutions autonomously without needing an expert to pre-configure them. And so ARC is envisioned to be the core enabling technology, bridging the gap from Industry 4.0 to 5.0. And this is operationalized by applying ARC at broadening scopes and scales from, for example, mobile service robots to shop floor scaling to coordination of fleets of assets to truly autonomous systems of systems, also known as cognitive manufacturing. So finally, if you wish to delve deeper into the technical details and theoretical underpinnings of the adaptive rational core, you may be interested in our book called The Road to General Intelligence, which was recently published at Springer and is available as open access too. So the link is right here, and this will tell you much more details about the technical underpinnings than you would ever care to know. So feel free to indulge. And we also have, but this is more a business website for this technology, agiarc.com. All right, thank you. And of course, I'll be happy also to take any questions.
So we have some time for questions. We'll do it the same way as we did yesterday. If you have a question, come up to the microphone.
Gary Marcus here. I was excited to see all that neurosymbolic stuff and surprised to see less emphasis on deep learning. I assume Jürgen's heavily involved in all of this. And I was wondering, have you used lots of deep learning stuff and decided you needed to go to this route? What's the backstory on how deep learning fits into this and why you went by, if not a neurosymbolic, I forgot your term, a very numeric symbolic route?
Yeah, so we view it as complementary. I mean, the deep learning stuff is not going to go away. It is still extremely useful for the immediate process, for really handling the, how do you call, the unwashed world of the raw sensory input and also an output. So I would say this AGI technology is like it's great for all the levels except level 0. That's still where deep learning stuff will shine and will continue to shine. So in our view, this is it all plays together. It's completely complementary.
Well, I mean, that's what I've been urging for years, but
preaching to the choir here.
Could have imagined that you would have tried to apply it throughout the stack and that maybe it didn't work, and that's what forced you in this direction, or like, did you start there? Like, how did you get there to something that's deep learning at level 0, but certainly in part symbolic above that?
Well, I mean, it's always there. I mean, it's still our bread and butter is still the deep learning techniques, and there's so many valuable applications there. And but we also observe that, you know, if you want to adapt to new requirements or to changes in the environment, the deployment environment, you need to retrain and this is costly, and then redeploy. So of course we want to speed that up, and we also see that the inferencing capabilities of deep learning techniques are limited. For example, if domains, many interesting domains have really long tail distributions, and this is just not where deep learning techniques shine. So we are of course thinking of how to handle these practical as well as fundamental issues, and so this is what we came up with to handle that. But still, all this higher level inferencing, causal reasoning, probably this will not this is not so applicable to really to the lowest levels. So at the pixel level, you're not going to do causal inferencing. So there we still need the deep learning stuff.
Exciting. I look forward to reading the book. Thanks a lot.
All right, thank you.
Hey, boss.
Hello.
Thanks your presentation. I have actually two questions.
All right.
In one of your slides, you were mentioning the phases in which your system deals with the process. It was slide 7, I guess.
This one, yeah.
Yeah. So
All
it
right.
starts from modeling the process, then recommendation and process control. So you mean that you have separated the phase of modeling and control.
Mm-hmm.
This is something very similar to what happens in control theory and what control engineers do. So the thing is, if we separate the learning process or modeling process and the control process, how the system knows that what it should learn, I'm wondering.
Yeah, of course, it will help to have some test bed. So either simulator or I say restricted or safe environment also to play around in. This is of course pulling it apart in phases. Maybe just to take a step back is also a bit of I say pragmatic thing to do, because when we talk to clients, there are when we say AGI is the future and it can do this and this great stuff, and then they're all like, yes, we want that. Yes, this is beautiful. This is exactly what we need. A system that does the work on command and always keeps learning on the job. And then we say, okay, we can actually do that. And then suddenly their face changes and they look scared. And I think like they're realizing, holy shit, these guys are serious. And so it's really scary for them, because then they start thinking about, how do we actually ever accept a system like that also is continually learning on the job? How do we ever accept that and deploy that in our plant? How do we certify that? How do we adapt our V&V procedures? Suddenly there's a lot of work that they are having to think of that needs to be different than what they've done before, when they were accepting control software that doesn't change after deployment. So that's why we pull it apart in these phases and make it more palatable and easier to get on with it, such that they can first, so that the system first is not connected to the plant, and that they can really look at the models that it generates and see, yes, this is actually how my process works, and I understand it now. I understand that the system understands what it is looking at, and now I feel confident finally to connect it.
Right, I see. And another question was that you mentioned that the rules are being modeled by linear transfer functions.
Mm-hmm.
So since your processes, as you mentioned, are dynamic physical processes, which are usually non-linear phenomena, how do you capture those non-linearities by linear functions?
Well, as I said, these rules, they are very, very fine-grained. Mm-hmm. So they're being massively chained and put in hierarchy. So from that perspective, it's not linear at all. It's just that the elementary transfer functions inside these very fine-grained rules, they are piecewise linear.
I see. Okay, great. Makes sense. Thank you.
All right, thanks.
We can even do two more questions.
Hi, Bas, Patrick here. I have one question to play devil's advocate here. To some degree, it makes very much sense to leave the low-level modeling to the deep, for instance, utilize deep learning models there. I'm more interested in what you are playing on a higher level, like if this model is say utilized to explain some of the conditioning capabilities of animals, say, what are you using on the top? Is there some kind of non-axiomatic logic, or is there some kind of are you passing gradients through the entire system, or how do you model learning?
Yes,
on the
definitely. Yeah, sorry, I could not hear everything. There was the sound was cutting out for a few seconds, but I understood. So your question is about the axiomaticity, and it is definitely a non-axiomatic. So meaning that whatever predictions or inferences in general are being made by these rules, they all come with their own confidence and likelihood estimates, and they don't need to sum to one. They can be conflicting, and the system can handle that. And when new information comes in that falsifies what the system has inferred, of course, then the system notices that and finds a way to resolve that.
Oh, interesting. And do you have some kind of inference control way of managing subcores? I would also be interested how you control when, like the abduction you mentioned, when you pass cores or subcores from one model to the next, so to speak.
Yes. So so the model consists of a massive amount of these rules. These rules, they are event-based. They can all fire in parallel as they want, based on whatever goes into the system in terms of inputs, in terms of other inferences, in terms of goals and sub-goals and constraints. And so these rules, they fire, they produce their inferences, and all these inferences, they all are coupled with an estimate of their of how good they are, which is based on how good the models have been, the rules have been in the past. Plus they're always also coupled to the reasons why the system is doing the inferencing. So if the system has multiple goals to chase, some inferences are coupled to because they are going towards one goal, some inferences are going to another goal. And if one goal is higher priority than another, for example, they get precedence in the scheduling of the controller into making more inferences. Or if you cancel, for example, one goal, if the owner says, drop that thing, don't do that anymore, just focus on the other thing now, then all these inferences, they all drop in priority, and they wither away, and the system focuses its resources on the other ones.
Very interesting. There are many parallels also with our work. Maybe we should follow up on this.
Of course, there are many parallels. I mean, we read each other's work as well, right? So
I agree. Yes. Thank you.
Bas, I have one question.
Yeah.
Does the system learn when to do certain kinds of reasoning? Do you have like a meta learning over the reasoning, or is the reasoning purely atomic and hand coded?
There are several templates in a way. So there are several types of inferences that can be made. So they can be predictions, they can be sub-goals, they can be assumptions, for example. So, and producing such inferences, they follow certain rules because it's logical to make assumptions under certain conditions, but predictions, they are made under other conditions. So so there's a limited set of inference types.
Is that a subject of learning? Can that be a subject of learning? In your current state of implementation?
So what is subject to learning actually is more like the state space itself. So the dimensions of the state space, these are subject to learning. So the system can incept new dimensions, so new concepts basically, and which are abstracting over certain regularities that the system observed. And this concept is then, of course, there's a couple of new rules that are tied to that to creating instances of those concepts and modeling when that concept also goes through phase transitions. And in that way, the system builds also hierarchies of concepts up to, you can think of them like higher and higher hierarchies. You can think of them as symbols, for example. So these higher level concepts, they change less often and they capture broader parts of the unwashed state space.
Thanks.
Yeah.
Last question from Jeff.
Hi, Jeff Thompson here.
Hi.
Thanks for speaking. I've already read your book and your website.
Cool.
So
Just now?
still interested in some details. One very fascinating thing is that you say that you have an operational semantics of the operation of ARC, presumably in something that looks like a cousin of replicode or something, or the code. Would it be possible to see that code that represents the operational semantics? That might be very insightful. Or if not, in general, is it possible that there could be a reference implementation of the logic, not the system that's the full-blown thing that will run a factory, on multi-core or something, but, something for us to really chew on?
So the operational semantics, they're open to, of course, we to our clients, we tell them exactly how, under what conditions, what inferences are made, and all the inferences that are made, they're all being traced by the system. And this is what we mean with reporting. So the entire all trains of thought of the system, they go into a database and they can be inspected and verified and audited by the owner at any time. And everything that the system thinks or does can be traced back through to answer the question, why did you think this was a good idea? Under what was the things you knew, what were the inferences that this was based on the knowledge that you had? So this can all be traced. This is all very explicit.